Good morning, everybody. Mr. Duncan is back. Okay, folks, so today's lesson is NMR part 3. And today what we're going to be doing is we're going to be focusing on questions is what we're going to be doing. If someone can lob onto the chat that the thing is working, I'm just going to extend my screen so that I can put my YouTube channel up there so I can see the chats that anyone asks. Please let me know that the sound's working, because that's the issue that I've been having, and having it there is really useful. Okay. Okay, my sound's working. Hey, John Moonhan, thanks for coming. I'm going to be going through questions today. Okay, let's crack on, folks. I still haven't sorted out my webcam, so I'm going to share my screen. I'm going to lob that up to that one there. No, hang on a minute. No, start with this again. Present. Share screen. Do my entire screen is that one. And then I do that to make my face disappear. Yay, so you're not seeing the ceiling. Okay, and if I leave it running, that means the sound should still be working. Cool, I'll hide this. Okay, so we're focusing today on questions, everybody, on NMR. And I know that actually this is the bit that everyone always asks me to go through in terms of how do I handle NMR questions. So today's lesson, NMR part 3, I'm going to be doing exam tips and questions. I've got 3 learning objectives. I need you, it's really useful to know the types of NMR questions that you're going to see, and to kind of have a basic understanding of how they're going to differ. John, can you do me a favor? Can you just give me a quick message on the chat again, just to say that you can still hear me? Last time I changed my settings and the sound vanished. Just say, yep, sound's working, if you can still hear me. That'd be amazing. Okay, so the first thing is, let's look at the type of questions. Then I'm going to give you some tips to be able to reduce the number of peaks. This is one of the most useful things that I can do with you folks, is recognizing that there's 2 things that you can do to cut the number of peaks that are commonly seen. And the last one is to understand Cyclos. Now, I haven't actually picked up any exam questions on Cyclos, I don't think, but I'll show you guys. I'll do some examples that I have in my head. So the types of questions that we're going to see in NMR is we're going to see essentially 2 different types of questions. We get what's called a build question. So there's what's called an NMR build. So a build is what they're going to do is they're going to give you questions where they give you the data, either a graph or a table, and they're expecting you to then construct your molecule based on the data you've been given. The other one is to interpret the data. So there's a build and there's a data interpret data. So those are the 2 styles of questions you've got. I will also tell you that these questions heavily link to the other parts of analysis. They commonly link the 2 together. Okay, so let's have a look and see where these come in. So the examples of questions that we're going to see. So example number 1 that I've picked. So compound E and F are esters with the molecular formula C5H10O2. And it then tells you that the proton NMR spectrum of E consists of 2 singlets, whereas F consists of 2 quartets and 2 triplets. Okay, so what I want to do is give you some exam technique for this. So the first thing I'm going to do is, here's all our data tables. I'm just going to scoot down to the bottom of my sheet of questions, and we can do some notes. So the first thing it's nice to then just talk about is this concept of them asking you to build things, because that's a build question. But it's recognizing what are called split pairs. Split pairs. Now, this is commonly not taught by teachers, and it's actually super handy. So if we go to what we were doing last lesson yesterday, and we were talking about our high-resolution proton NMR, and we talked about ethanol. And what we did is we spoke about the idea of the fact that if you're not joined to a carbon, then you're going to be a singlet. So this one comes immediately out as being a singlet. But these 2 are now adjacent to each other. What that means is that they're going to interact with each other. And this one here is going to be the original peak plus 2 clones from the adjacent non-equivalent hydrogens. So this one's going to be split into a triplet. This one, on the other hand, this one, and it's going to have an integration, by the way, an integration of 3. This one on the other side is going to be an integration of 2. So the integration is going to be 2 for this one. We have the original peak plus 3 clones from adjacent non-equivalent hydrogens. So it looks a bit like this. So we get to see our triplet. This is our triplet, and we saw these last lesson, and our quartet. So this idea of split pairs is the fact that if you have splitting, this is a nota bene, if splitting occurs, you must have at least. The reason for this is because in order to split, you need non-equivalent adjacent hydrogens. Yeah, non-equivalent adjacent hydrogens, which means they must interact with each other. So for the example, if I just do a couple of examples, methanol shows no splitting. It's going to be 2 singlets, peak number 1 and peak number 2, integrations 1 and 3 respectively, because there's no non-equivalent. But as soon as you add a carbon next door, you get 2 splittings. So what you can do is you can call these split pairs. So examples of split pairs include, so if you get the most classic one I love to talk about is a triplet. This is a great piece of information because a triplet split pair immediately tells you something. It tells you, number 1, it is in the middle of the molecule. It's not at the end. The reason why is because these carbons must be adjacent to each other and they must be non-equivalent, which means R and R must be different. So this will be R1 and R2, and these must be different. Yeah, they're different from each other. Yeah, R1 and R2, because they are non-equivalent. If they were equivalent, you get split cancellation, and it wouldn't, but they're going to be different. But the key thing that I need you to take away from this is the recognition that a triplet is a middle section, and it's going to be a CH2CH2. That's because this one gives you an original peak plus 2 clones next door. There's your triplet. This one does the same thing. The original peak plus the clones from the adjacent non-equivalents. This will give you a triplet. So that's the first split pair that it's worthwhile talking about. The next one is another massively classic one, the triplet quartet. So the triplet quartet is another classic split pair. Yeah, triplet quartet. These guys are going to be the end of a molecule because this is going to be CH2CH3, and it is the end of a molecule. And the reason for this is in order to get a quartet, and it's interesting to then assign who's what, because I think the most common thing here is that people will put the quartet with that guy because there's more H's. This is not the case. The reason being is this one here, I'll do this as carbon number 1. This one's going to have the original peak plus 3 clones from the ones next door, from the 2. So that's going to be your quartet. And it will have an integration of 2. So it'll be a small quartet. The next one, carbon number 2, is going to be split by these guys. So this one is going to be the original peak and 2 splits next door, integration 3. So it's interesting to be able to pick up these split pairs, but then it's also just as important to start assigning the splitting to the person who's doing the job. Okay, another classic one, less common. Those 2 are the most common split pairs that you're going to see in the whole of A-level chemistry. They're super common. We see them all the time. But there are other ones which you can talk about. If you get a doublet quartet, that's another common split pair. So this is a doublet and a quartet. This split pair is telling you that you're going to have a carbon next to a carbon. And because it's a quartet, it's going to be the end of a molecule. And then the other one's going to have only one next door. And these are going to be your R1 and R2, your different R groups. Now, they don't have to be R groups. Sometimes you can pick up an alcohol group is attached to it, maybe. But what we know is I shouldn't put them as R. It's actually a bad thing to do. But the thing is, it can be Rs. You can add a C double bond O here. That would work. Yeah, because there's no hydrogen on that carbon to split the guy next door. Yeah, we could also add an alcohol group. That's another classic group to make an appearance. But the point being is this structure here is coming from this split pair. So recognizing split pairs has huge value because what it does is it cuts down the amount of time it takes you to solve a question. Okay, so we've covered a little bit of split pairs. You're going to see these as you do questions. The next thing it's nice to talk about is how to reduce peaks. These are all exam techniques, by the way. So the title here of this bit would be How to Reduce Peaks. Okay, so to reduce peaks, we've got two options. Option number one, which is our survey said most common, is branching. I'll show you the example of this, is branching. So if I did something like this, if I did pentan-1-ol, yeah, so there's your organic naming. I'm tempted to give you an A2 naming to do. All of these are H's, and of course, we're talking entirely about proton high resolution here, but we can also do it in terms of reducing peaks. It's actually C13 as well and low res. So I'm going to ask you to pause the video and tell me how many peaks in C13 would you get in this particular molecule? Have a go. Okay, so in C13, carbon 13, we're going to get, there is no symmetry here, so we've got a maximum number of 5. 5 peaks. If we were going to draw the graph of it, we know that this one's going to be furthest from 0, yep, and they're going to get steadily closer to 0 towards TMS as we go down the molecule. And it's all to do with the environment being different as they're distant differences from the O, different distances from the O. So I'd like you then to have another challenge at this. So let's now talk about proton. Pause the video and tell me how many peaks will you see in both high resolution and low resolution? How many environments are there in this? Pause the video, have a go at it, unpause when you're ready. So the answer to this one is there's going to be 6 peaks in this one. The reason being is these guys are all in the same environment. These guys are in the same environment. These two are in the same environment. This one's in the same environment. This one, these two are in the same environment. And I'll do this one as a star in the last one. So we've got 1, 2, 3, 4, 1, 2, 3, 4, 5, 6 peaks in proton, only 5 in C13. We've got these enormous numbers of peaks. Yeah, we can talk about the splitting of each of one of these if you like. So this one, of course, is going to be split into a triplet. This one's going to be split into a multiplet or a quintet. A sextet, if you like. The reason being is the original peak plus 1, 2, 3, 4, 5 clones. This is going to be a sextet, but you'd just call it a multiplet. Yep, so I'll put it as an S if you like, S/M, either one. This one's going to be a quintet or a multiplet, also allowed. This one's going to be another quintet, and this one's going to be a triplet. And the last one, a singlet. It's nice just to do these kind of exercises. If you're able to do this, you're halfway through the battle of doing NMR. Okay, so I want to now reduce the peaks. So I'll set you a challenge. I've given you the #1 method of reducing peaks is branching. So if you want to reduce this peak, let's stick with the carbon 13 just for this particular case. I would like you to reduce the peaks, please. Instead of 5, I want 4. Pause the video now and give me the structure that gives 4 peaks in C13. So we want 4 peaks, and you can unpause it when you're ready. Okay, so here's the answer. What I want to do is I want to branch it. So I'm going to chop one of the carbons off. Instead of pentan-1-ol, I'm going to turn this into butan-1-ol, and I'm going to take the carbon that I chopped off the end, and I'm going to add it to a branch at the end. Now, this is a key trick. You've got to put the branch at the very end. The reason being is if you don't put it at the end, you're going to have issues because it won't be the same distance from the O. This branching that I've just done reduces the peak number by 1. So this is now going to be 3-methyl-butan-1-ol. And this one, these two now are in the same environment. Yes, there's a partial sim line. That means I'm now going to have only 4 peaks in the C13 instead of 5. Sorry, I've just done this as a proton. I've said C13. These two are the same. So there's carbon number 1, carbon number 2, carbon number 3, carbon number 4. 4 peaks. Integrations. Sorry, carbon number 1. Integrations. So C1 would have an integration, if I just put integration of 2. C2 is going to have an integration of 1. C3 integration of 1. C4 integration of 1. It's just nice to do it. It does the same job for the proton as well, because what you realize is that the protons are doing exactly the same thing. You realize that once you start picking up these tricks, it speeds up. So this is the first one, and then we've got second, third, fourth, and fifth. I've cut it by 1. So, okay, there's the next one. So let's cut it again. What I'd like you to now do, please, is do exactly the same thing, but this time I want you to cut it down to 3 peaks. Yeah, so let's do 3 peaks. So guys, pause the video and then give me I would like the structure is displayed, please. Give me all displayed, not skeletal. I hate skeletal. Give me displayed picture, please, giving me only 3 peaks. I'd also like you to name it, please. Pause the video now. Okay, so the answer to this is going to be, I'm going to chop another carbon off. Yeah, I'm now going to propan 1-ol, but I'm going to add my 2 branches. And I'm putting them on the end so that they interact with the same one at the end of the molecule. These 3 are now becoming the same environment. They are now equivalent carbons and equivalent hydrogens. Yeah, so this one in C13 is going to be giving us carbon number 1, 1, 1, 1. They're all exactly the same. This one's carbon number 2. This one's carbon number 3. I've asked you to name it. So the correct name here is 2,2-dimethyl-propan-1-ol. Yeah, is everyone okay with that? I would also say that you don't need you don't need the 2,2, but just put the numbers in. Yeah, it's better to always include the numbers. I've only had 1 person on the chat, by the way, folks. If someone could just confirm with me that the sound is working, that would be really, really useful, because I'm really worried that this isn't actually working properly. That would be great. Okay, so it's nice to see 3 peaks coming up, and you kind of grasp this concept of branching now. It's a really useful skill to learn because, as I said, they love to do this, and it applies not only to the builds, but it also helps when you see these integrations. Because if we look at this from a proton, the proton's more, I said 3 peaks for carbon, and that works for the carbon. The protons is a bit more tricky. We know that all of these H's are in exactly the same environment, which means I'm going to have an integration of 9. It's going to be massive. Yeah. And in fact, that hydrogen there in red is going to be a singlet. Yeah, it's not going to get split. And the reason why is because the adjacent carbon has no hydrogens on it. So this is going to be a strong singlet peak with an integration level of 9. Yeah, then the second carbon has no hydrogens on it at all. So the peak now vanishes. This one, which I will do in blue, these hydrogens here now make an appearance with a tiny little peak of integration 2. So this has got an integration of 2. And of course, the great thing is it's also a singlet. The reason being is nobody on either side has a carbon with hydrogens next door. So that's also a singlet. And on the last one is going to be a baby singlet as well for that one. I should do it in a different color. I've actually put them in the wrong order. I've put them in the wrong order when it comes to the graph, because in reality, that H, the yellow H is going to be furthest downfield. The blue H's will be further downfield from the red one, but less than the yellow one. You kind of get the picture. We can draw the graph if you want to, but it's also a singlet there as well. Integration 1 this time. So it's a fun game to play. It's nice to put this onto the graph. TMS, tetramethylsilane. The more I say this to you, the more likely you are to remember it. It's 0, non-toxic, inert, nothing lies to the right of it, strong singlet peak with no splitting. It's really useful. Easily removed, loads of we love TMS. And so what's going to happen is the yellow one's going to be way downfield, being on the with an integration of 1 because it's on an oxygen. I have warned you though that alcohols are a little bit variable. The next one is going to be closer with an integration of 2, but still a singlet. And the third one, of course, is going to be again a singlet integration 3. We can start looking at the data in terms of how you give the ranges of these things as well. There's also a nice thing to mention that there are 2 questions when it comes to using the data book, which is in terms of data book questions. Yeah, the data book questions, Q's, these tend to be, the first most common type is to, it says quote the range. Yeah, that's a super question, very common. Quote the range. Quote the range in NMR. In NMR data. Yeah, quote the range. The other question is suggest a value. Now, those are actually suggest a value. These are not the same questions. Really, they're not. The reason being is suggest a value means suggest a value. It means give a single value. You're not allowed to give a range in question number 2. You have to give a number. And the great thing is, which always throws students off, you just give any number in that technically within the range. I would always recommend you to pick the middle of it though. It's always better to go for the middle of the range than to go top and bottom. And that's kind of common sense, but students still do odd things at times. Okay, so the next thing is it's nice for me to now mention Cyclos. Joe, before I do that, I'm going to have a look at these data. It's nice for me to start applying these questions to data. So let's go all the way to the top. Let's look at this from a proton NMR perspective. I'm going to copy that. I'm going to put it next door so we can actually see them. I'll put it here, paste. It's really useful to use, and we can suggest and quote values for the range and the data. So the yellow one, which is the alcohol group. So I need to find the H. Now, if you notice, one of the things that's not really highlighted often by teachers, because we kind of expect you to, we kind of think that you're just going to be able to use this thing, but in reality, you do need lessons on how to use the data books. Notice that these H's are in bold. That's because they're telling you which H's to look at. This is really, really important. That H, that H, that H. Notice that the alcohol and ether one aren't highlighted. I always think that's quite an interesting thing there, that they don't do that, but it is what they're meaning. Yeah, anyway, keep going. So the highlighted H's. Cool. So let's now try and pick up some of these. So let's stick with the yellow. So the yellow was an alcohol group. So if they ask me to quote the range of the OH alcohol here, I'm going to pull out a ruler. And you need a ruler in your exam. Please, please, please. You need a ruler. It's really important for NMR. And it's really for these questions. Because if I'm going to they ask me to quote the range. Yeah, I'm going to draw my lines down here. Yeah, and I'm going to draw the line there. There's my range. And I know that this is really tricky because there's no sliding scale on this. Yep, so you kind of have to get used to that. I've made them too small now. And I know it seems mad for me to do this, but 1, 2, 3, 4, yeah, give or take. So that's going to be about 3.9. Yeah, and then on this one, I'm going to say that one's going to be about 1.8. But if I go 1.9, I will be inside the range. And it's quite nice to do that. I probably would actually quote 9 on that one, probably would. But the point I'm trying to make is that being inside the range is always better than you don't want to go outside it. So if I move that to 3.8, I'm guaranteed to get this mark in the exam, because what I'm actually quoting here is this. This is the range I'm actually quoting in my answer. And that range is inside the range within 0.1 of the one on the data table. This guarantees me the mark. Being 0.1 inside it, it's really useful to know that, guys. Super useful. Okay, so there's our OH alcohol peak. And so if I was going to quote this in the exam and they asked me to quote the range, I'm going to quote 3.8 to, what was my other one? 1.9 to 1.3. I actually said 3.8 and I wrote 3.9 to 1.9. There's my quoted data range there. Yeah, is that the one that I wanted? Yeah, 1.9, 3.8. Nice. Okay, and then if I want the blue one, this is a bit more tricky because now this is the blue one here. Shouldn't do that. This is the blue one here. I now need to quote the hydrogens that are next door to an alcohol and the oxygen. So let's have a look at this. The oxygen and the alcohol, sorry. So let's see if we can find that. So we're scanning through on a carbon next door to it's here. There it is. Yeah, this is the carbon. I'm going to zoom right in. This is the carbon next door to the alcohol or an ether or an ester. Yeah, could be an ester as well, but it's on the O next door to it. So this is the range I'm quoting. As I said, it's useful just to talk these little bits through. I'm going to end up having to do a fourth lesson on time. So that's the H I'm going to quote. And once again, take out my ruler. And you really do need a ruler, folks. Like, I can't stress this enough. The amount of times that students kind of look at this data book and then just start quoting numbers drives me nuts. So this is 2.8 to 4.2. I'll go inside it. I'm going to go 2.9 to 4.1. That puts me inside it. Yeah. So this one's going to be, I've forgotten already, 2.9 to 4.1. 2.9 to 4.1. I don't know what my laptop's doing. Weird. It's because I've got my pen in my hand. It's thinking I'm putting the pen on the table. 2.9 to 4.1. If that's the range, these are the range questions. If they ask me for a value, I'm just going to whack a value dead in the middle of this. So this is 2 and 4. So I'm going to go for 3. 3.0. It's a great range. Oh, my laptop's doing something weird. And the next one, I'm going to quote again, dead in the middle, 4 to 3. So I'm going to do 3.5. Yep, there's that would be the value I give, but the range is at the top. So do just bear that in mind. If we look at the last one of these CH3s is integration 9 for the red one, because remember the C13 doesn't make an appearance because there's no H's on it. Yeah, so I'm now doing the one next door. Okay, let's see if we can track that one down. Now we know it's going to be further away. It's going to be closer to 0 because it's further distance from that electronegative oxygen. And what we realize is the one that's doing it is actually straight flat bang your alkane group. Yeah, this is a carbon next to a carbon. Yeah, and there's with nothing else attached to it. So that's perfect. So we're quoting, notice that the box is just past 0, which is super stupid. I'm going to quote the range as 0.1. I don't quote 0. That's a trap, by the way, and a very common A-level trap to boot. They do like doing that. It's a really clever question, this, because this ranges from 0.1 to, you can't quote 0. Heck, I've seen students quote negative numbers because they read the graph off with their lines. I totally get it. And if anything, my method of using the ruler is going to almost encourage it, but you can't. This box, students often then say to me, so Mr. Duncan, why do they tend to put it then beyond 0? It's a really difficult question. The reason being is that why do they go beyond 0? There's probably going to be examples which actually do something strange and go beyond it. But I don't want you to, if they ask you to quote this, it's a common trick. Go for 0.1, and now this one's halfway. We know that's 5. Yeah, so this is going to be about 1.5, 6, 7. It's about 1.7. I'll quote 1.6. That's always a good number. Is that 1.6? Yeah, 1.6. It's a good number. 0.1 to 1.6. Range, if I was asked to give a value, I go 0.8. Yeah, so just to make you aware of it, it's useful to have a practice using those and to look at questions. Okay, move my ruler out of the way. So now that we've got a kind of a basic idea of this, it's nice for me to then show you this being applied. I'm just going to get rid of my ruler. Let's apply this to the question I've just been given. Compound E and F are esters. So instantaneously, I've got to be careful because they want proton quartet. They want me to give both. So I'm going to say, let's just scratch that and say E. They're both esters. So I need to have this group. Yep, that's important. And I've got 5 carbons, and that ticks off my 2 oxygens. Yep, I've got 4 carbons to go, and E's spectrum consists of 2 singlets. Well, in that case, I will just add a CH3 onto the end here, because that means it must be a singlet because it's directly next door to an oxygen. The next thing I need to do is I've still got 3 carbons to go. Yeah. So let's just have a look at how this pans out, because this is the thing of NMR is a puzzle. I've got 3 carbons to go. This doesn't work. It's so nice to do these games and to play around with it, because what you realize is here's your first peak and they're all in proton NMR, and it needs to be a singlet. Well, I was hoping that was going to be another carbon to go on, but the problem is I've actually got here I've actually got, I'll add those H's in to make this obvious of what I'm circling. Yeah. I've actually got, I've not got, those two are the same. Yeah, but that's a third one. I've got 3 peaks. That doesn't work. So what I'm going to do is I'm going to flip this over. Instead of putting the branches on the back end of the ester, I'm going to put them at the front end. Just going to spin it round. Yeah. So let's turn this ester. Let's just whack an NH on the end of that as if it was made from methanoic acid. And let's just add all of our carbons onto this guy. Bracket, remember, branch it will reduce my peak number. I want as many branches as I've got, and that now works. So I've now picked up my correct ester. So my 2 peaks, and that's a singlet because there's no hydrogens on the carbon next door. This one, no carbons on the central one, but these ones are all the same. Yeah. So we've got an integration of 1 to 9, both singlets. Nice. So there's A. So branching reduces peaks. Now F, let's have a look at F. So F consists of 2 quartets, 2 triplets. Ooh, I've got my split pairs. Now, just to tell you, by the way, did you notice when I ran through my split pairs, I didn't include a quartet-quartet? That's because you can't get it. A quartet-quartet would suggest that you've got 3 next door to a 3. Yeah, you can't do that because if you did that, you've got ethane, but then you get split cancellation anyway. So we don't get it. So this is actually 2 split pairs of triplet quartet, triplet quartet. So that means I can immediately, if I've got a triplet quartet, I can immediately draw this structure. And it's telling me that I've got 2 of them. Let's run it. Do you see now it's how useful it is to have these split pairs in your head? Oh my God, easiest NMR build ever. Yeah, so straightforward. That's awesome. All from one simple fact. Split pairs rule. I love split pairs because it makes the game so much easier. Recognizing that you can't get a quartet-quartet eliminates that as an option. You can't have a triplet-triplet if you can't have a quartet, if you can't have 2 quartets because the triplet-triplet would be on their own. So it must be a triplet-quartet times 2. It's cool. Love this game. So much fun. Cool. And there's your ester of ethyl propanoate. Love it. Oh, how would I name this one? This would be 2-methyl. Ugh. By the way, that's beyond A-level naming, but it's a good one to have a go at. This is 2-methyl. No one's going to like this. Methyl, ethyl. Yes, that's right. Methyl, ethyl. Yes, I know it sounds weird. I'll explain it in a minute. Methanoate. It is beyond A-level, but I can show you the example they will give you. A common A-level ester naming is just to get rid of that one there. Just so you know, just doing a little bit of organic naming. If I do that, yeah, that's a very common one. This now just becomes methyl, ethyl, methanoate. Yeah, I'll show you where the name comes from. The 2 is what is this bit makes it entertaining. I can highlight the structures and where these come from. 2-methyl comes from this guy. And then the by the way, can actually be either or, can be either or of them. This one then is the methyl bit, and then this one is the ethyl part. Esters are weird. The reason being is what you have to imagine is the full length of the ester is that's the longest chain I can make. These 2 are both branches. Oh, you could technically call it a dimethyl. Ooh, isn't that funny? I think I've just spat out a correct. I've just made a correction. This would be a dimethyl ethyl methanoate. Nah, easy fix, Mr. Duncan. Well done. Isn't that nice? The correction in the name came from me explaining it to you. It's nice that. So anyway, it's nice to talk about it. As I said, other examples of those, please do the practice. Next. So the reaction of but-2-ene with chlorine produces 2,3-dichlorobutane. State the number of peaks, their integration ratio, and any splitting in the proton NMR spectrum of 2,3-dichlorobutane. Right, now this question here, guys, is you're asking to interpret data. That's the question. And it needs a very specific style of answer. Here's what I'm immediately going to do. So I'm going to add this into my note. Data interpretation. Stage 1, draw it. You need, if the diagram, epicos. Hello, hey, Mr. Duncan, it's Oliver. Hey, Oliver. Hope you're doing well. Nice to see you still doing your amazing YouTube lectures. I've just started them again, Oliver. I haven't done them in 2.5 years, so I thought I'd do my NMR sequence. I hope you find it useful. Are you doing A2 this year, Oliver, or have you already finished? Anyway, so data interpret questions. The first step is to draw it if they haven't given it to you already. Sometimes they give you it pre-drawn and then you just label it. But if they haven't, you need to draw it. Really important. So I'm going to straight off draw 2,3-dichlorobutane. Yeah, I'm going to draw this all out. Everything goes on. Yeah, there we go. Let's lob these on here. Oh, it's so nice to see you, Oliver. It's been years and years. Cool. So there's now what I need to do is it now says state the number of peaks. What I'm now going to do is notice that this is proton NMR and they're asking us for splitting. I was in your class 2 years ago. I'm now doing university. I'm doing engineering. You clearly forgot me. No, Oliver, of course I didn't forget you. As if. Of course I didn't. 2 years ago. That was in Malaysia. I know. Good grief. It's good to see you though, dude. I hope the engineering is going well. So what I now need to do is, first of all, notice there's an instantaneous symmetry line. Yeah, so it's going to have fewer peaks than we thought. Lots of people start saying all kinds of crazy numbers. It's got a molecular symmetry line. These two are the same. I'm going to label that there. And then all of these are the same. They're all exactly the same. And by the way, this is how I answer the question. I actually draw it like that with squares and circles. I actually do that, folks. The examiners will love you for this. Yeah. So then what I can do is I can say bullet point. I'm going to say 2 peaks. State the number of peaks. 2 proton peaks. And then it's nice to explain it. 2 non-equivalent environments, proton environments. Nice to put it properly. Proton environments. Next. I'm then going to say, so I'm giving the number and then explaining it. That's how you guarantee your answers, because, you know, it's saying state the number peaks. It's not saying to explain it, but it's nice to do so. The next one is, it then says the integration ratio. So I'm going to say that the integration ratio is going to be 6:2. But I'm then going to tell them who it is. So I'm going to say 6 circle ratio to the square ratio. I'm actually going to draw it like this so they can see it. Yeah, 2 to 6. Love it because they add together. Next thing, any splitting in the peaks? And the answer is yes, there is going to be splitting. So what's going to happen here is, now this is kind of interesting because I almost want to go for split cancellation here. But split cancellation is not on your specification. So what that means is I'm going to just flat out ignore it. And what I'm going to do is I'm just going to say that the square peak, so square hydrogen, if you want to, by the way, you can label them as environments 1, and you would do it in your thing, 1, these are all the same. Yeah, environment number 1, environment number 2. Yeah, so I'd put square, or in hydrogen number 2, environment. I'm running out of space because I've been putting in questions, haven't I? Environment number 2 is going to be split into original peak plus 4 others. It's going to be a multiplet. It's going to be a... See, the thing is that I want to call it a quartet because these two are in equivalent height. These are in the equivalent things, which means it's going to cancel. I want to say it's a quartet. We'll have to look at the mark scheme. But this one's going to be it's going to be a multiplet because it's going to be 5, or a quintet. Maybe that's why it's given us in terms of saying it's a quartet. The other one cancels. Multiplet. I'll do a multiplet. Yeah. And I'm going to say because it's got... Oh, you see, but then you're saying because it's got 4 non-equivalent hydrogens next door. No, I'm not going to do it. I'm calling it a quartet. I'm going to do split cancellation. Yeah. And then environment number 1 is going to be split into a doublet. We know that's true. Yeah, because it has, and I'm putting the because as useful. Yeah. It's got 3 non-equivalent adjacent hydrogens. Yeah, this one is a doublet because it has 1 non-equivalent, adjacent hydrogens. Yeah, I hope you're finding that one okay. It'd be interesting to find that mark scheme for that and to see what they actually, did they want a quintet? I kind of want to check. And by the way, if any of those haters out there sit there and email me saying, Mr. Duncan, why are you getting this wrong? I don't pretend to be flawless. Far from it. I just like to practice. And if you don't appreciate my videos, don't watch them. That's no skin off my teeth. It's definitely off this one, though. Let's see if I can find this question. It won't take me very long, I promise. Please just bear with me for 1 second. It's worth checking these. There it is. No, mechanism. No. It won't take me very long, I promise. These are all NMR questions. I'm looking for the... Oh, hello. Nope. Oh, esters. There's the ester picture. It's probably going to be just after that. There. That dichloro give the mass spectrum. Number of peaks. There it is, you see. Didn't take me that long to find it. So this is question 16C. I wonder if they accept both answers. 16C. There we go. I was right. So the ratios are 6:2 or 3:1. 2 peaks, doublet, and a quartet. 2 or 1 other one. Cool. So they actually wanted the quartet. I was correct to switch it. Nice. Because it actually I changed it because I didn't like the explanation. Trying to say, we always say that it's split this many because there are these many non-equivalent adjacent hydrogens. Well, that one's equivalent, so it's going to disappear. Yeah, and I went for the quartet. It was the right decision to make. Let's go for the next one. I hope you found this useful. This is how you should structure this. Yeah, I can also talk about the chemical shifts. There are other questions that I will do in my next webinar. I'm very aware. I don't know how long my webinar's been going on for now. Let's just quickly check, shall we? This has been 41 minutes. I'm going to do one more question, folks, and then I will, I'll do one more question. And then I'll leave the video. Okay, so just quick multiple choice. Compounds, I've got methyl ethanoate, ethanoic acid, N-ethyl ethanamide, an amide, and ethanol chloride. So the question says, which of these is the most, nice to do a different question on a different topic. This question, A, comes straight out of carboxylic acid derivatives. Which one reacts most vigorously with water? And acyl chloride all day long. They violently react. They violently react with everybody, but water especially, with misty white fumes of HCl, which forms methanol when refluxing with sodium hydroxide. Sodium hydroxide is going to hydrolyze it. Well, if I did sodium hydroxide with this, I'm going to stick the Na there. Nope. It's going to be the top one because it's the only one with a methyl group. We're going to split the ester and turn it into methanol and sodium ethanoate. Again, we're going to split the amide, turn it into the salt, the carboxylic salt, and the amine. The acyl chloride will act as an acid. It will turn into, again, another carboxylate salt. So the answer here is A, splitting the ester. Next one has at least one triplet in its high-resolution proton. One triplet. Okay, so it's nice to do environments and splitting based on structural. So this one's going to be a singlet. This one's got no H's on it anyway, so this one's also going to be a singlet. This one's going to be a singlet. This one's going to be a singlet because the carbon next door has no H's on it. These ones are going to be a triplet because there's 2 next door. These ones are going to be a quartet. Excuse me, everybody. This hydrogen is not on a carbon, so it's going to be a singlet, and this one's also going to be a singlet. So this one has a triplet. Yeah, the next one, singlet only, so the answer is C. Nice, always a fun game. Let's keep going. Okay, so this question's just asking you to use the data book. Oh, really nice for me to use this question, by the way. I actually want to build. No, this one's better. Let's go for this one. Compound B, another isomer with the molecular formula C6H12O2, contains a ring of 6 carbons. Here's my Cyclos, everybody. Okay, so quick note on Cyclos. So Cyclos can also cut peak numbers. I told you earlier on in the lesson, the 2 methods to cut peaks, in my notes were further down, In the two methods to cut peaks, you had two choices. Did I write this down? Branching. I didn't give you the number 2. Okay, so just underline this. The second way, number 2, the second way to reduce peaks. Reduce peaks 2. Yeah, number 2, hashtag 2, is to make something cyclo. Yeah, go cyclo. And the reason for this is it creates symmetry. So here's a great example. If we go for, and I'd like all of you, please. I've gone for the 6 purely because the last question had 6 in it. It was quite nice to do it. Right, guys, how many peaks in carbon-13, please, would you expect in this one? This is a great one to do, by the way. Pause the video. How many do you think? And the answer is 6. Yep, this is going to have max, so C13, this is going to have 6 peaks. Because the person of interest, even though it's not electronegative, the molecule's not symmetrical. They're going to be really, really, really close. And in fact, most of them are going to be within the same range, but they're all different distances from this C double bond, which means they're going to be distorted. They're going to be pushed a little bit downfield, just a little bit. And so just, yeah, anyway, neat question. And we're going to get 6 peaks. If I now branch it, we talked about the branching. If I branch this alkene, I could reduce this. Check out this. If I just put all 6 like that, I've reduced this from 6 carbon peaks down to 2. Yep, ratio 4 to 2. So that's 2,3-dimethyl-butene. That one is going to have 2 peaks only. But the other thing that I can do is I could turn this into a cyclo. I could turn this into cyclohexane. And if I do that, my peaks go to 1. Isn't that cool? Branching will take you so far. Branching will take you so far, but in reality, cyclos can go an extra 1. I can cut this all the way down to a single environment by going into cyclohexane. So let's go back to the question. Yeah, it takes practice, folks. NMR is not something you learn in a day, just to let you know. Let's go back to this question because I really like it. So we've got a cyclo, and we've got compound B, C6H12O6. The carbon NMR spectrum has 2 peaks. 1, now that is really interesting. What an interesting bit of data. And it's in C13. So where the hell is 69? Where's my data? That is really interesting. You don't often see this. 69. So 69 this is 70. So the 69's here. Now notice that it could be either an alcohol or this one. Well, jackpot. Let's scrap that guy. There was no Cl or Br in it. What that means is this has got to be joined to an alcohol group. Nice. Okay. So going back to this. So we've now figured out, based on that little bit of data, that it must be on, I've totally lost it. There we go. Must be in, this is a carbon bonded to an alcohol group. And there's only 2 peaks, and it's told me cyclo. Let's just, for fun, let's just go straight into 6 in a ring. Yeah, we've been drawing 6 in a ring for benzene for ages. Yeah, but now the thing is, I need to have the minimum number of peaks down to 2, and I have got 2 oxygens in here. So if I put the alcohol group here and an alcohol group here, in carbon-13, there's my symmetry line. I'm going to have 3. That doesn't work. Let's move it. Let's move it down to here. Yeah, let's put it to here. Yeah, there's my other one. So if I now split, there's my symmetry line. I now have 1, 2, 3, 4. Damn, it's getting worse. Let's get rid of that. Let's move it all the way to the bottom. And all of a sudden, you realize that there's now 2 sim lines. Sim line number 1. Sorry, I'll do the sim lines in red. Sim line number 1. Sim line number 2. Jackpot. I've only got 2 peaks. And I'm done. It's all a game. These are puzzles. I know I make it look easy, folks, but I've been doing these for 20 years. Yeah, it takes practice. What I would say is when you're doing the practice, make sure that you do one question and then go and check it with your teacher. Yeah, go and make sure that you're getting it right. Once you've got 2 or 3 that you're getting consistently correct, by the way, the mark scheme is always useful. And then if you're getting them wrong, go and talk to your teacher. But anyway, I'm going to leave it there today, folks. Next lesson, I'll do one more lesson and I'll do a whole load more questions, specifically the really big build questions. And I'll talk you all the way through those. But I will end my lesson today. It has been a blast. Hi, sir. Hope you're doing well. So glad that you are back on YouTube. Will you be doing AS videos anytime soon? Yes. Do you like me to do a paper 1 today? I can do a paper 1 today from AS. This afternoon I'm free. Oh, I can put myself back on. Yay! I'm back. 50 minutes. I'm so sorry, folks. Yeah, this afternoon I'll do a paper 1. Anyway, guys, I really hope you find this useful. Have a great rest of your day.